Hello everyone, this is Professor Roman. Welcome to the 25th video in my video lecture series, An Introduction to Discrete Mathematics. In this video, we're going to talk about multinomial coefficients. Now, the binomial coefficient n choose k, as we know, counts the number of ways to choose a subset of size k from a set S of size n. Another slightly different way to look at that is that n choose k counts the number of ways to divide the set S into two disjoint and distinguishable subsets. The subset of k elements that we do want and the subset of n minus k elements that we don't want. And I use the term divide rather than partition for two reasons. First of all, one of the two subsets might be empty, which is not permitted in a partition. And also, as we talked about before, the blocks of a partition are by definition indistinguishable. Whereas in this case, the two subsets of elements we want, elements we don't want, are distinguishable by that feature. So I'm going to have to use the term divide, form a division rather than partition or form a partition. Now, more generally, we might want to divide a set S into two or more mutually disjoint, distinguishable subsets of given sizes. So, for example, suppose we had 100 people and we wanted to choose 25 of them for some particular reason, and then we wanted to choose another 20 of them for another particular reason. So we've chosen 45 people out of 100. We still have 55 people left. Just to make this a little more tidy, we'll just assume that we've also chosen the rest of the people, the 55 people. They're the people we don't want. And in that way, when we form these divisions, we have a set of mutually disjoint, distinguishable subsets whose union is the entire set S. Okay, so it's just more convenient to do that. From the perspective of just choosing elements from S, all we're doing is choosing some elements for the first subset, then choosing some additional elements for the second subset, and so on. And because of what I just said, we're going to continue that process until all the elements of S have been chosen. This is actually quite a common task, not just in mathematics. For example, this is exactly what a professor does when he or she assigns grades to the students in a class. The professor chooses those students to receive an A based on their test scores, their performance in class, then chooses those students who receive a B, and so on. And as long as every student gets a grade, we have this sort of division of the set of students into mutually disjoint, distinguishable subsets. Look at this example. We have the underlying set ABCD. The ways to divide that set into three mutually disjoint, distinguishable subsets, A1, A2, and A3, of sizes 2, 1, and 1 respectively, are listed in this table. Now, if you look at the first two rows, we have this A1 is AB, A2 is the singleton C, A3 is singleton D. In the second row, A1 is the same, but I've interchanged A2 and A3. These are distinct subsets of this division, a number of ways of dividing S into three mutually disjoint subsets. But if we were to think of this as partitioning, these two would be the same because then the subsets would be indistinguishable. So that's the key difference between what we're doing now and partitioning a set. Well, so the question becomes, how many ways are there to divide a set into mutually disjoint distinguishable subsets? And we specify the sizes of each subset. Here's an example that illustrates not only the specific case, but the general formula. The president of a country has a 13-person cabinet from which he wants to form 3 advisory boards. A 7-person domestic advisory board, a 4-person foreign affairs advisory board, and a 2-person general affairs advisory board. How many ways can that be done? Well, this is a job for the multiplication rule. The independence requirements are satisfied. There are 13, choose 7 ways to pick the 7-person domestic affairs board. And then from the remaining 6 people, or 6, choose 4 ways to choose the foreign affairs board. And finally, from the remaining 2, we have to pick both of them for the general advisory board. And so it's the product of these binomial coefficients. Now, when you write them out as factorials, there's a lot of cancellation. You get a very nice looking formula, 13 factorial divided by 7 factorial times 4 factorial times 2 factorial. This is the general pattern, so this deserves a definition, some terminology. If we have non-negative integers m1 through mk and their sum is equal to n, then this expression, which is called a multinomial coefficient, is equal to, by definition, n factorial over the product of the m factorials. Okay. So that's what we ended up with here. And I suppose you could read this, I don't know, n multi-choose m1 through mk or something like that. Multinomial coefficients only make sense when the sum of the lower numbers is equal to the upper number. So I'm not going to say that over and over again. I'm just going to assume that whenever I write a multinomial coefficient, you can assume that I've checked to make sure that the sum of the lower numbers is equal to the upper number. Okay? And a binomial coefficient is a multinomial coefficient. When you write n choose k in terms of factorials, it is n multi-choose k n minus k. So just as in the previous example, this multinomial coefficient counts the number of ways to divide a set S of size n into k pairwise disjoint distinguishable subsets, say A1 through AK, of sizes M1 through MK. It also counts the number of ways to choose M1 objects from S, then choose M2 of the remaining objects from S, and so on, until you've done that k times, made the k choices. So these two are really saying the same thing in a different way. And the proof here is essentially the generalization, direct generalization of the proof in the example. So I'll let you read this for yourself. The one place where you may have an issue is showing that all of this collapses into this, but we have discussed a proof technique that will help you do that. So the number of ways to divide this set, 1 through 8, into 4 mutually disjoint. I get criticized a lot for not using enough commas. Distinguishable subsets of these sizes, 5, 0, 2, 1, is this multinomial coefficient, which works out to be 168. We've seen that the binomial formula tells us how to expand the powers of a binomial, x plus y. The multinomial coefficients will tell us how to expand powers of a multinomial like this. So we just write out the terms, the factors. There are n factors here, all the same. Now, when this is expanded, the terms will have this form where the exponents are non-negative integers whose sum must be n. These are formed by choosing I1 of the n factors and pulling out x1 from those factors. Then I2 of the factors pull out x2, and so on. So the total number of factors of this form will be the multinomial coefficient. And that gives us the multinomial formula, which looks like this. And here's an example. If you want a particular coefficient for this term, then you put to this multinomial is raised to the 10th power, so 10 goes in the upper number, and these 4 exponents go at the lower numbers, 12,600. Now, the real interest for us in multinomial coefficients is counting things. We've seen it can count the number of ways of dividing a set and so on. We've counted the number pnk of ordered arrangements, that's n lower factorial k, ordered arrangements with no duplicates, right, from a set of size n. We've counted the number of unordered arrangements and choose k. So how does the multinomial coefficient fit into this pattern? Well, we have shown that the multinomial coefficient counts the number of ways to choose M1 objects from S, then M2 objects from what's left in S, and so on. But we can view that in a little different way. We can use these K choices to choose locations in a word of length n, n being the sum of these m's. So we choose M1 locations. Here's our alphabet. We choose M1 locations for the letter B1. Then we choose M2 locations for the letter B2, and so on. We have filled in n locations. And we have constructed a word of length n over this alphabet. And the multiplicity of B1 is M1, and so on. The multiplicity of BK is MK. So just to give you an example, if the alphabet is WXYZ and the multiplicities are 2, 1, 0, 3, we have to choose 2 locations for the W, 1 location for the X, 0 locations for the Y, and 3 locations for the Z. So we have a total of 6 locations to choose, so we're going to get a word of length 6 with 2 copies of W. So we'll take a look at this one. The 2 copies of W come at the end. 1 X, which is right here, and 3 Z's. Here's another possibility. Same multiplicities. So the multinomial coefficient counts the number of words, this one, the number of words of length n with fixed multiplicities over an alphabet of size k, because there are k multiplicities. Now, just to clarify something before we state a theorem here, there are several ways to describe words with fixed multiplicities. They're all equivalent, but I want to talk about them. One way to describe this object is start with a multiset M with an underlying set of size k. A word with fixed multiplicities over this alphabet then is simply an ordered arrangement of the elements of the multiset. The multiset already has, every element already has a multiplicity in the multiset. So we've taken care of specifying the multiplicities when we specified the multiset. All we have to do now is take the elements of the multiset, including their repetitions, and order them. And we get a word with fixed multiplicities. The multiplicity of each letter in the word is equal to the multiplicity as an element of the multiset. Okay? Another way would be to say that a word with fixed multiplicities over this alphabet, with these multiplicities, is a word over the alphabet where each letter appears as many times as its multiplicity indicates. This is probably the most direct, simplest way to make the description of a word with fixed multiplicities. The problem is you have to write all this out each time, okay, which is generally not a big deal. A third way to do this is to say that a word with fixed multiplicities is over an ordered alphabet. So our alphabets are ordered, and then our multiplicities can be ordered. So we have a k-tuple of letters in the alphabet and a k-tuple of natural numbers for the multiplicities. And again, each letter appears as many times as its multiplicity indicates. And I don't want to make a big fuss over this. These are three different ways to describe the same concept. They vary only stylistically. Sometimes it's easier to use one, sometimes it's easier to use another. Okay. So now we can summarize what we know about multinomial coefficients. This multinomial coefficient counts 1, the number of ways to divide a set S of size n into k pairwise disjoint distinguishable subsets A1 through AK of sizes M1 through MK. 2, the number of ways to choose M1 objects from a set S of size n, then M2 of the remaining objects in S, and so on. 3, the number of words of length n with fixed multiplicities M1 through MK over an ordered alphabet A1 through AK. Now, the point of ordering is simply to match the elements with their multiplicities. I guess I should have said that up here. Okay, that's the only reason to order the alphabet. It's convenience. Okay, doesn't add any new mathematics. If you order the elements of the alphabet, you don't have to write something like this. You can simply write this. Okay. And from this last description, we can get a formula for the total number of words over A of length n. We know it's k to the n for other reasons, but we now know it's also the sum of all the multinomial coefficients. Okay, we've already seen why all this is true, but just for practice, I want to give you a different proof of part 3 here, because it illustrates a useful type of reasoning, and it's always nice when you have two different types of reasoning that confirm each other's results, you know. So let's prove this one again. So let X denote the set of all words of length n with fixed multiplicities over this alphabet of size k. Now we want to find the size of X, and the idea is to decorate each occurrence of a given letter, say A sub I, in a word W in order to remove the duplicates, because we're more comfortable counting permutations where there are no duplicate letters. So for example, here's a word AABC, ACBC. I put in some extra spaces just to make it easier to read. It has length 8. And the way we're going to decorate the letters is with superscripts. They're not exponents, they're just superscripts. So A will get the superscripts 1, 2, and 3. B will get the superscripts 1 and 2, and C gets 1, 2, and 3. So we start with 1. For each letter, we start with 1, and we use as many superscripts as the multiplicity of that letter requires. Okay. What is the decorated word? It's a permutation of 8 distinct objects. Now, a letter that appears with multiplicity m can be decorated in a lot of different ways with the numbers 1 through m. In fact, in m factorial different ways. So just as a very simple example, the word AA can be decorated in 2 factorial ways. Put the 1 on the first A and 2 on the second A, or start with the 2 and then use the 1. Okay. How many ways then are there to decorate a single word? Well, it's going to be the product of the factorials of the multiplicities. Just like here, 2 factorial, because this letter had multiplicity 2. Okay. And now you can see how the multinomial coefficient is coming into play here. The decorating process defines a function from the set X, whose size we're trying to figure out, to the set of all n factorial permutations of the decorated letters. There are n of these because the sum of the m's is equal to n. The inverse of this function is just erase the superscripts, right? This is a 1 to n factorial correspondence. And so the 1 to k factorial counting rule tells us that the size of X is the size of the set P here, n factorial, divided by this product of factorials. And that's the multinomial coefficient. So we get the same result in an entirely different way. But this process of decorating is useful in many contexts. If you have a bunch of things that are the same and you wish they weren't, this is a technique that can oftentimes be instructive. Not always, but here are a couple of examples. They're pretty straightforward, so I'll let you take a look at them yourself. Let's take a look at our progress so far in finding counting formulas. And this is shown in figure 66 here. We have dealt with words of size k. This is S is a set of size n words of size k with unrestricted multiplicities, and as I discussed before, that means just the natural restrictions. There are n to the k such words. This comes directly from the fundamental counting principle or multiplication rule. The words of size k from a set of size n with fixed multiplicities we've just discussed. That's the multinomial coefficient. Words of size k from a set of size n with no repetitions allowed, those are just the permutations, and so that is p n k, which is n lower factorial k. And multisets of size k taken from a set of size n, again with no repetitions. Those are just, because of the no repetitions, the multisets become sets. In fact, subsets of S. So that is Cnk, which is n choose k. This entry here is quite easily explained. These would be multisets of size k from S with fixed multiplicities. Now, it would be useful for you, I think, at this point to stop the video and see why, if you can convince yourself why that number is 1. But all you really have to do is ask yourself the following question. From the set containing A, B, and C, how many ways are there to choose 4 A's and 3 B's? Well, since the choice is unordered, these are multisets, there's just one way. A, B, B, B. That's it. It's only one way. So that fills in this cell here. In the next section, we're going to deal with this relatively simple formula that belongs here, multisets of size k from a set of size n, no restrictions on multiplicities. Okay, thank you for watching this video, and I hope to see you in the next video.